Okay, so in the last lecture, we were discussing the solutions of Schrodinger equation for stationary states of hydrogen atom. And I skipped the solution and requested you to go through the solution yourself. And we were discussing the final solution that, comes out. So if I recap the method of solution, so what we actually do when we solve for hydrogen atom is that we are able to represent the solution as product of spherical coordinate theta and phi and the radial coordinates. And the reason for this breakdown is very simple. And the reason is this, that the potential that we are working with only depends on the magnitude of the radial coordinate, and it doesn't depend on theta and phi. And that's why we were able to break down the solution as product of theta phi dependence and the radial dependence. Now, since in the theta phi part, there is no radial part involved, and there is no term coming from the from the potential, it means that it's independent of the potential. So whenever you will have a problem with spherical symmetry, where the potential is not dependent on theta and phi, any problem, its theta phi dependence will always be, made separate. And the solution of the equation is in what we call spherical harmonics. And that solution itself is actually a product of theta dependence and phi dependence. Phi dependence is very easy. It's just exponential iota, some integer into phi. And the theta dependence is in terms of associated Legendre equations, where theta varies from 0 to pi and phi varies from 0 to 2 pi. And the solutions, have some integer some integers in them. For example, there is an integer m, then there is integer l in the solutions, and those integers are there to make sure that the solutions are single value. That if you rotate by 2 pi degree around z-axis, that's the angle phi, then your solution should have the same value as before. So that's why there's that exponential iota m phi dependence. And also to make sure that the solution remains finite, the associated Legendre polynomials have finite number of terms. So and also the periodicity with respect to theta. So because of those properties, the solution have those integers which we usually refer to as quantum numbers. And then the radial part also has integers in it, n and l, where again we have a polynomial in R, and it's a polynomial simply because we don't want our solution to blow up at infinity. We want the solution to go to 0 as we approach infinity, to make physical sense, so that the overall wave function remains integrable over the whole space. And when we change potential, but if we still keep it, dependence on radial coordinate, we'll see that spherical harmonics will just keep coming as it is, and only the radial part solution will change. And if we, make our potential dependent on theta and phi, then we will have to solve Schrodinger equation again, but using some other technique, because then we might not be able to separate our solution into R, theta, and phi. But in most of the problems that we tackle, we are able to imagine that nuclei is, somewhere close to the origin, and our electron is far away, and the potential is only dependent on radial coordinate, and it's not dependent where the electron is on the surface of a sphere. Okay, and at the end, we were discussing that since the wave functions that we solved for the hydrogen atom, their linear combinations also form a solution. So instead of expressing solutions as a product of functions for a given value of n, l, and m, we combined some of those solutions in a particular way, to get what we call real wave functions, a real solution. But the purpose of combining them is not to have been to work with real function. The purpose will actually become apparent when we do molecular mechanics, because these wave functions have those symmetries that we require in molecular bonds. And we will also see some of that thing today when we work with the graphs. So before I go and start discussing variation and perturbation theory, I would like to spend a little bit of time on understanding these wave functions again, and their especially how to visualize them. And then we'll go ahead and start working on the variation principle that will be very useful for multi-electron atoms. Let me start sharing my screen. Okay, so we were discussing real wave functions, hydrogen-like, and I have copied them here. Just to recap a little bit. This 1s is when n is 1, l is 0, and m is 0, which we also refer to as psi 100 wave function in the language of NLM. But just to emphasize, we haven't talked about the spin of the electron yet. We are not considering that degree of freedom. So couple of weeks down the road, we will include spin as well. But for now, we just work without spin. Similarly, this 2s wave function is for n2, L0, M0, you refer to as 0200 or 02s, or just simply 2s. Okay, this 2pz is psi 2. Now n is 2, but l is 1, and m is 0 for this. This is also referred to as 2pz or psi 2pz. Sometimes it's also referred to as 2p naught, just to emphasize that the value of m is equal to 0. And this 2px is actually the sum of psi 2 1 1 and 2 1 minus 1. So this is for m1 and this is for m minus 1, and this 2py was with minus sign. Of course, we had an iota here to cancel the iota that we get from here. And the reason for this is that when m is 1, the phi dependence is exponential iota m phi. So when m is 0, there's no phi dependence. When m is 1, we get exponential iota phi here, exponential minus iota phi here. Everything else is the same. So when we add them, we get cosine 2 phi. So we get cosine phi. With here, we get sine phi. And if realize that r sine theta cos phi is just x, so that's why it's also referred to as 2px. Similarly, 2py, and so on. Okay, and just to briefly describe the psi NLM is RNL and YLM. So these are the wave functions. Okay, so similarly, there are other coordinates. For example, this dz square is when n is 3, l is 2, and m is 0. This dxz, dyz, they are for m plus minus 1, and these are for m plus minus 2, because you see cosine 2 phi and sine 2 phi coming here. Okay, and again, these subscripts, they refer to the fact that the product of x and z, where x is r sine theta cos phi, z is r cos theta, their product xz is this term. Similarly, y is r sine theta sine phi, and xy is just this product of x and y and so on. But we'll see that these subscripts are helpful actually in more ways than simply this labeling. They also help us in visualizing these orbitals. Okay, one more point about these real wave functions, and that is that our psi and Lm wave functions, they are eigenfunctions of three operators. They are eigenfunctions of Hamiltonian operator, of course. We get energies, which are functions of n coordinate, and they are also functions of the magnitude square of angular momentum. We get L into L plus 1 into, psi Lm again, and L psi here. And these psi's are also functions of Lz operator. And we get this h cut square, h cut m psi. But these real wave functions, they are eigenfunctions of h, they are eigenfunctions of L square, but they are not eigenfunctions of Lz. And you can see why. Because Lz's eigenvalue is h cut m psi. But now we have, this pz orbital, this px orbital, which is sum of the, let me actually just write it here. So this 2px, this was obtained by 2p m 2 1 plus 1 and 2 1 minus 1. So m is 1 here, m is minus 1 here. So this doesn't have a single value of m. They have same n, same L. So that's why they are still eigenfunction of h and eigenfunction of L square, but they're no longer eigenfunctions of m. Simply because, they're no longer eigenfunction of Lz, because now we have two different functions that have different values of m. Okay. So any question about these wave functions? All right. So if not, let's talk about visualizations. There are several ways of visualizing multidimensional functions. You see, if we have one dimensional function, let's say y is equal to f of x, and if this is real, it's very easy to visualize it using a graph like this, because all you do, you change x, and whatever f of x comes out, you just plot it. But when you have multidimensional functions, then this becomes problematic. For example, there are like some ways. For example, if you have this z, which is function of two coordinate x and y, now there are a couple of ways of visualizing it. One is that you use this 3D map. This x and y is this plane, and your z is a third dimension. So you put different values of x and y, and you get a sort of a surface, and the values on this surface as a function of different coordinates in this xy plane, they give you x. That's one way of visualizing it. Another way is, we can prepare some density maps. For example, you just have some x and y plane, and then, or you can use color map, right? So red color maybe mean that the value of function is 0. This color may mean, this is maybe +2. So this color, may mean that function is +4. So this black color may mean that the value of the function is -1, and so on. So you prepare a color map. But you also have to think about a little bit old fashioned when you think about these visualization ways. People have access to color printers and these things only recently. So most of the last century and even before, when we used to print books and things, people only have access to black and white color. So many visualization methods, they still assume that you are going to print this thing in black and white only. So color schemes usually still not that popular. So that's why there's another way that we can represent these things, and that is what is called the density map. So in the density map, we can put dots and to represent the density of the function. So more dots would mean higher density and higher magnitude, and smaller number of dots means low density and low magnitude. And this thing you can use uh, uh, for positive real value function, because then to represent negative you might have to invent something else, maybe another color or something like that. So most of the time density maps are used to represent to visualize functions with positive real values. So usually we plot absolute values with these density maps. So this density map actually has a benefit that we can transport it into 3D as well. For example, if I want to show the probability density of one s orbital, I can use the 3D density map like this. Okay, since when we talk about this r square function, it is have highest magnitude at a certain distance, and then it has a lower magnitude inside and lower magnitude outside. So maybe we can use some density map where density increases and then density decreases. So these density maps can be used in 2D and can be used in 3D. But if your function already is a function of 3 coordinate, for example, we have the psi mod. So this is function of 3 coordinates. So we can either represent it a density map in 3D, but still when we print it on a book, the book is evidently a 2D construction. So usually instead of just giving these 3D plots, what people do, they give its different cross sections. Okay, for the same function we can have an xy cross section, we can have a yz cross section of the same function. Because if you have, let's say, a pz orbital, so pz orbital have a high density along this axis. So if we along z axis, but in xy plane it is isotropic. Actually in xy plane it is 0, sorry. So in xy plane, the pz orbital, the psi function is 0. So what you do that, but if we have xy xz, in xz it has the same shape as in yz. So it means, and in xy it's actually isotropic, but it's 0. But if you go a little bit up in parallel to xy plane, a little bit down to xy plane, you will see that it is isotropic, that it is same irrespective of the direction. So you will have to use your visualization, your imagination, to combine these 3 planes and think about this variation of pz orbital in space. So you might think it is some structure. If z-axis is pointing upward, that is increasing upward and downward, and it is isotropic in xy plane. It's sort of figure of revolution around z-axis. So for this 3D dependent functions, we can use their cross section in different planes to represent or to visualize these wave functions. Okay. All right, so let me now discuss these functions. And there is actually another construction as well. It's called a polar plot. Let me discuss as well, because most of you might be familiar with this, but some of you might not be, so it's worth, repeating it. So a polar plot is a plot like this. Suppose you have a function, I don't know, some f of x, y, and some x, y square, etc. What you do, you actually use polar coordinates and convert into function of r and theta in this plane. Let's say I'm only talking about 2D plane right now, and then you plot it for a fixed value of r. Okay, r is fixed, so when r is fixed, this has become some function of theta only. Suppose it is sine square theta, cos theta, something like this. Then what you do, let's say you start from here, and this is the direction for theta is equal to 30, this is the direction for theta is equal to 90, and so on. So this is how you keep going, and you plot this function like this. So what you do, you make a table with the one axis theta and the other axis f. So let's say theta 0, theta 30 degree, theta 60 degree, and so on. And you compute the value of function. Suppose it is 1, 2, 1, 0 at 90 degree, and so on. And then you plot it like this. You say, okay, at 0 it is 1. So let's say this is the distance from origin, which is proportional to a unit 1. Then at 30 degree, the function is 2. So then at 30 degree, if this much is 1, then so this is 2. And at 60 degree, it's 1 again. So at 60 degree in this direction, it is this point. And at 90 degree, it is 0. So this is the point at 90 degree. And then you join these points like this. So this is a polar plot where along any given direction, the distance of the point on the curve from the origin gives the relative magnitude of the function. So it means that this function is maximum along this direction. Okay, because this is the point which is farthest away from the origin. So similarly, if it's something like this, it could be like this. And in this direction and in this direction, the function is 0 because the curve in this direction collapses to the origin. So this is how the polar plot is defined. Everybody okay with the polar plot? Okay, perfect. जी
सर ये पोलर की बात कर रहा हूँ सर, ये थोड़ा मुझे नेगेटिव वाई एक्सिस के ऊपर भी इसकी वैल्यूज आ सकती हैं?
बिल्कुल आ सकती है, क्योंकि नेगेटिव वाई एक्सिस पे एंगल जो है वो 370 डिग्री होगा।
लेकिन सर वो हमने पढ़ा था स्फेरिकल सिमेट्री के अंदर, तो उधर तो 0 से पाई तक एंगल नहीं होता पोलर एंगल का, उसकी वैल्यू जो होती है।
ये थीटा जो है वो मैं अभी वो स्फेरिकल वाले थीटा को रेफर नहीं कर रहा, दिस इज जस्ट सम एंगल इन दिस प्लेन व्हिच गोस फ्रॉम 0 to 360 डिग्री।
ठीक है सर, ठीक है
अब सही। अगर आप वो स्फेरिकल वाला थीटा लेंगे तो इट्स 0 to 30 डिग्री। हां
यस, 0 to pi,
sorry 0 to pi। Okay, then there's another type of map which is frequently used. It's called a contour plot or contour map to represent these 2D functions. And this is better than polar coordinate in one sense. In polar coordinate, we actually have only one variable, theta. The r variable is fixed. R is at a fixed value of some fixed value. But if you have some function, something that is function of two coordinates, and you want to be able to see the variation of function with respect to both, another option is use the contour plot. So contour plot, as you know, works something like this, that you draw contours or lines in this plane, and each line is labeled. For example, this is labeled as -10, this is labeled as 100, this is labeled as I don't know, 0, this is labeled as 50, and so on. And these labels correspond to this value. So like this, that this line, this -10 line is labeled -10 because on this line the value of the function is -10, which means that if you enter the x and y coordinates at this point into this function, the answer is -10. If you enter x and y coordinate of this point on -10 line, the value of the function is -10, and so on. Similarly, on the line which is labeled 100, the value of the function is 100 at all of the points that lie on this line, and so on. So to be precise, all of these contour plots should be labeled, but most of the time even these labels, are omitted. But using many functions, you can put these labels on. If you many graphing softwares, you can put these labels on. But this is a nice way of visualizing the functions as well. Okay, so everybody is able to comprehend now these plotting techniques? Okay, so one thing I would like to emphasize now, that when you see a map which seems to represent a 3D function, never think of it as the map or plot or shape of that function, because this is only giving partial information. And you are able to see the map in this way only because you are plotting a certain quantity. So to imagine the function, you still have to use your mind to visualize what the function is saying. So you can't really talk about the shape of the function or the graph of the function, etc. You should always talk about, if you see the contour map, you should talk about the contour plot in this plane of this function. Okay, not that, okay, this is the shape of that function or this is the shape of that function, because all of these graphs are only giving partial information about that function and not the whole picture is there. Okay, so let's talk about a couple of things. And actually, let me talk about now these orbitals, and let me discuss some of the plots. So let's copy this one again. Now I'm going actually to use either the density plot or the contour plots to represent some of these functions. So let's talk about this 1s orbital. You see, it only depends on r. And because it's independent of theta and phi, it means that if I draw its polar plot for 1s orbital, I should get a circle, because for any theta and phi, it's giving one same magnitude. And it doesn't even matter if this is xy plane or yz plane or zx plane. And even if I draw its contour plot, I will still get circles, right? Because whenever I put it equal to something, r is constant. So at different values of r, I get, the same circular thing. The same is the case with, 2s, but little bit more complicated now. This is still independent of theta and phi. So it means my contour maps and my polar plots would all be function of, will not be function of theta and phi. Okay. So for 2s, but if I draw its polar plot, I will get a circle. Okay, because when I put it when I make r fixed, you remember for polar plot r is fixed at one value. So if r is fixed, it's now independent of theta and phi, and I get a circle. But if I draw its contour plot, now it would be something like this. I will have some contour inside, some contour outside, and at some value of r, my contour would be labeled 0 because this function can be 0, and at this contour it might be okay, I don't know, 0.1, but this contour would be 0.3, and this contour might be 0.5, and then this contour 0.3 again, and so on. And I see that this is a contour where the probability is maximum because this 2s has a contour whose magnitude is maximum. Okay, so
कंटूर प्लॉट है, इसके ऊपर हमारे एक्सिस क्या रिप्रेजेंट कर रहे हैं और जो हम हर कंटूर को वैल्यू दे रहे हैं, ये कौन सी वैल्यू है? ये आर की वैल्यू है?
नहीं, जो पहली बात एक्सिस आपने चूज करने हैं, सिंस इट्स अ 3-dimensional function x y z, so for contour plot you let's say choose that this is x axis and this is y axis, and you will have to fix z something. So let's say z is 0, so it means I'm plotting in xy plane. Now this function psi 2s is x is something, y is something, z is 0, and what I do that I give different values of x and y and compute the value of the function. So these values that are present on the contour, these are the values of the function itself. Okay, so this is, in this case, these are proportional to probabilities because it's mod square. We know that gives probability density, right?
ठीक है सर, सही है.
Okay, so this has also these circular shapes. Let's now talk about this PZ. So PZ is r cos theta, and there is an exponential term like this. So let's first talk about the polar plot of PZ. So polar plot of PZ. So we will actually have a function which is only proportional to cosine theta, right? Because in PZ, this is all function of r, and if I fix r, this is just a constant. So for polar plot of PZ, I only have cos theta. And the polar plot of cos theta, something like this. So let's say I am in YZ plane. So theta is 0 here, theta is 180 here. So theta 0 is 1, theta 90, it is 0. In between, it's like this. And then when theta increases from 0, it's negative. But it increases in magnitude. So I'm actually plotting cosine theta mod. So similarly, you can plot on this side, okay? So this is the polar plot of PZ function. And remember, this is not the shape of the function, or this is not the orbital of PZ. This is just the polar plot, because this is plotted for fixed value of r, which means that it's 0 along the y-axis. Similarly, if you make this x-axis, it will still be 0, but it's maximum along z-axis. And we can plot its contour plot as well, but I'll plot it using Mathematica in a little while. So let me actually just talk about the contour. If you just talk about the contour plot, we're essentially talking about the spherical harmonic part only, okay? Because r of r is function of r, and that is fixed. So if you plot only spherical harmonics and forget about the radial dependence, we are actually talking about the polar plots of the wave functions. And that's not usually what we do in when we really are interested in talking about the probability density distribution of different atomic orbitals. And that's why this is a picture that you will not see much. We will be talking with pictures that carry more information than this one. Actually, let me show that, because I have prepared a Mathematica file for you. Can see. Let me just share the whole screen. Okay, so can you read what I have written on this screen or not?
We can, sir.
थोड़ा सा zoom कर लें लेकिन.
Let me see how I can do that. Size. Control A. Okay, is it better?
Yes sir, ठीक है.
Let me do it a little bit. All right. So you see, I have prepared these functions. So this Z is 1, but later on, I have kept this Z so that you can use it for hydrogen-like orbitals as well. For now, I'm taking this A to be 1 because this will make our life easy and everything will be okay still. And then this is R10 is something that I have defined as a function in Mathematica. You can define with R underscore, whatever the variables that you plan on using, put an underscore, and then use this colon and equal, and then we can write the function. By the way, if you, for this course, I think Mathematica would be the easiest because most of the time we would be interested in simple things. I know some of you would be, finding it easier with MATLAB or maybe Python if you're well versed, so that's okay. But if you don't have any programming experience or have forgotten everything and you just want to do it for this course, probably it's better if you stick with Mathematica because most of the time I will be using Mathematica for this course and sharing these notebooks with you as well. Anyway, so these are the radial dependent functions that I have already that are first the solution of hydrogen Schrodinger equation, and I have given self-explanatory labels. So this is R and L. So the first index is value of n and the second is the value of L. So these are the functions, and this is here just part of what you are supposed to do in your homework. So these are different radial distribution plots that we have. If you want to plot the probabilities, you can probably use R square with them. So then you can also plot the probabilities if you want to see the everything. Plot range to full. So this gives the full plot. Anyway, so these are the functions that we have, and then these are spherical harmonics. This T represent theta. So I just took it from table 5.1. So these are the spherical harmonics that are there, and I'm giving polar plot just for you guys to visualize them. And let me use the absolute values. So this blue circle is S00, and then one of them is S10, the other one is S11. I think this horizontal one is S11 and the vertical one is S10. And you see in the polar plot, if you want to do the polar plots for hydrogen atom, you don't even have to consider the radial part. You can just use these functions. Let me give this plot legend to see what is what. Okay, so you see this S10 is lying along the horizontal axis and S11 is along the vertical, simply because its starting theta is equal to 0 from the horizontal axis. When you transport this theta to the spherical coordinate, you should imagine that this horizontal axis is actually the vertical axis, because in spherical harmonic, we measure theta from the horizontal axis. So just to see the next absolute S11, and let's see what is S20 look like. Okay, so you see S20 has 4 lobes. So it's mostly along the z-axis. So z-axis is horizontal this time, and it has some lobes, along the xy plane. In some of the books, these contour plots are given as shapes of these orbitals, but really speaking, they're just the contour plots of the spherical distribution at a fixed value of r. They're not showing the whole picture. Okay, so let's now see the contour plots of different functions, and for that, I'm using modules like this. For example, let's construct this psi 2py. So it has x, y, and z as input, and then r is just square root of x square, y square, z square. This t theta, t is this, that's angle theta, and it's z over r. And then this p is angle phi, it is x over r sine theta. And then this fun is whatever function we want to compute. So let me start one by one. So let's start from psi 2z. So psi 2z is actually r21, and it has m0, so it's like this, and m0, so exponential iota is also it's 0, and it's returning this thing. And let me plot it in the YZ plane. You see what I'm doing, that for X, I'm putting 0. So this Y and Z are variable, and I'm specifying Y and Z as -10 to 10. And then I'm making a contour plot. Oh, sorry, this is 2PC. All right, so this is the contour plot of PZ orbital, and I can take the cursor to different places to see the magnitude of function at these contours: 0.16, 0.14, 0.1, 0.06, 0.04, and so on. So this is what gives us the contour plot of PZ function. And I actually want to plot Px, Py. And let's see, this is Px. And by the way, you can check in other planes as well. You want to see what the function look like in xz, xy plane. So let me make this x, and z. I can put z 0, but then there at some places the function is 0, and it complains that it's r becomes 0 at some points. So Mathematica complains that it's not right. So let me make this. You see, it's symmetric in that just at x is equal to 0.1. So in the xy plane or parallel to xy plane, it's a symmetric function. It's the same in xy plane. Anyway, let's come to Px, and Px has R21, but S11, and this is cos phi. Just check. So Px is sine theta cos phi. so that sine theta is part of S11. So this S11 has sine theta in it. So this cos phi is coming because we created this px by adding so this is symmetric in YZ plane now. Okay, and if I want to have, so in X, this was symmetric in XY plane, and this is symmetric in YZ plane. So in XY plane, this has the same shape, and you see that this horizontal axis is the x-axis. Let me put x first. So horizontal axis is x-axis. So it's exactly the PZ function, but it is along x-axis now. It has its high density areas along x-axis, and in the XY plane this was symmetric. And if you just plot the psi 2p1, so psi 2p1 as exponential iota 1 phi. Okay, and this is 2p1, and let's know. You see, this is symmetric in XY plane, but this one has lobes along this one, and if I make it, let's see it in the YZ plane. So in the YZ plane, it has this lobe, and in the XZ plane, in the XY plane, this is pretty strong. So this is like a donut which is lying in XY plane. So it's in the YZ plane. Let's go back to XY plane.
Say for contour and polar plots, do we need any additional libraries in Python?
I think you should be able to do them using matplotlib.
Okay, yeah. So there's no additional library required.
Yeah, I think so. Okay, so let me now talk about this thing that I was talking about earlier, that why we need, these plots. So the PZ has contour plots like this. That it has high probability. So this is Z axis, and this is either X or Y. So it has high probability for finding electron here and here. But this P1 is like this. So P1 and actually plus minus 1 both, they are like these donuts in this XY plane, and their probability decays as we go up or down along Z axis. So that, and they have this Z axis symmetry, so that's why they are function of LZ as well. They are eigenfunction of LZ. But when we study bonds, so for example, we have a hydrogen atom here and a hydrogen atom here, and the electron comes closer, so they find bonds like these. And similarly with other when we have more nuclei, so for these bonds we need orbitals like these that are along x-axis, or maybe if there's another atom or this atom is lying along z-axis. So to have these symmetries along x-axis or y-axis or z-axis, we need orbitals that are solution of Schrodinger equation, but they possess these xyz symmetries. So that's why instead of working with these orbitals, then we construct px and py orbitals, and similarly other real orbitals that possess these certain symmetries along X, Y, Z, etc. axis. That's the main reason. But if we have just single atom, hydrogen atom, then of course we can either work with 2p plus minus 1 or 2p xyz. It doesn't really matter. Let me go on and do some plots for a bit more complicated orbitals. Let's take this one. Let's say we do 3D orbital, and for this let's take 3D z square. So for 3D z square we should have n3, l as 2, s as 2, and since this z square, m is 0 for this, so this is 0. So if let me put m0 here, I can just actually remove. So this is that 3dz square orbital. 3dz square. Let's say what does it look like? So in xy plane it is symmetric. Let's check it in YZ plane. So in YZ plane it's like this. So this is the y axis and this is the z axis. Let's increase the graphing area. Okay, so here it is. So it has these two lobes along the z axis, along y axis, which is horizontal because y comes here first, and then z axis, which is vertical, it has these two big loops. So let's see for 3D. The 3D XZ has R32, but then S is 21, and it is made by adding. So it is M1 phi and 3D. So in the YZ plane, it is, it has only one lobe, but let's check it in the XZ plane. Okay, is there anything wrong that we have done? So this XZ, this 3D should have N3, and it has L2. L2 is d orbital. Now here L is 2 and N is 1, M is 1. And when M is 1, we add them and we get cos phi. So ZX. Let's see if S21 is defined. Okay. Is this S21 is 15 sine cos? Yes, okay. Let's check the R32. This is R32. That is 72. R square exponential minus ZA3A. Yeah, so So 0, let me put some 0.01.
सर आपने यहाँ दोनों z और z कर दिए हैं.
हाँ अच्छा ये x and z. Thank you. Okay, so you see that in the xz plane it has these 4 lobes, and let's check in xy plane. Okay, so it has, in xy plane it has these 2 lobes, and in the xz plane it has those 4 lobes, and then it has 2 lobes in the other plane. So by combining these, you can construct a visualization for these things. So actually, I think we can construct contour plot 3D for x, y, and z. Let's see if I can do that, because then we should be able to get a 3D picture. Because of R0, it's complaining at some point, but I hope that it gives the plot. Okay, so while it's working out, I hope that by this you get an idea how to visualize and understand these plots. Let me copy the plots that are given in the book for some of these orbitals. Okay, so you saw that when we were plotting the xz plot, it was similar to this thing. Okay, the only thing is that for the for 3D z square, we saw that our plot is similar to this, and then for x square and y square, these lobes are exactly along xy axis, and when it is xy, these lobes are inside these planes. So that's why this designation also helped, that when it is xy, it means that the lobes are inside this plane, in the xy plane. When the label is xz, that actually means that if you plot it in the xz plane, the lobes of high density, high probability contours are inside these xz planes. Similarly, when it is the yz sub-label, then it is in the yz plane. And then the other two are plotted here. This is dz square or d naught that we just saw. It has these high probability contours along z-axis. And for x square, z square, it has these contours along the axis, not inside these planes. Okay, so it's still working. Anyway, so any questions about these plots and visualizations?
सर जो आपने होमवर्क में क्वेश्चन दिया था, इसमें हमने सारी s की वैल्यूज प्लॉट करनी थी. उसमें हमने सिर्फ उसको एक एक्सिस पे r रखना, दूसरे पे उसकी वैल्यूज रखनी थी, सिंपल प्लॉट करना था ना, लाइन प्लॉट्स बनाने थे, कोई पोलर वगैरह तो नहीं करना था उसमें.
बिल्कुल.
तो सर ज्यादातर जो थी वो आपस में काफी मिक्सअप सी लग रही थी, इनमें बहुत ज्यादा डिस्टिंग्विश करना मुश्किल था, काफी करीब करीब थी लाइन से.
कोई बात.
ठीक.
सो जस्ट उन दोनों एक्सरसाइजेस का जो मकसद है वो आपको ये एक मैसेज पहुंचाना है कि इसके तमाम होमवर्क्स में कोई प्रोग्रामिंग का छोटा छोटा सा पार्ट इस तरह से होगा, सिंपल. जी दिया.
सर हमें ये जो इसके लिए कोई ट्यूटोरियल आप करा सकते हैं, क्योंकि पहली कोडिंग तो उस पे कर ली थी मैटलैब पे, लेकिन ये थोड़ा डिफरेंट लग रहा है, तो अगर कोई ट्यूटोरियल या कोई हो तो हेल्प हो जाएगी।
ठीक है, मैं अब्बास से कहता हूँ कि वो एक डिस्कशन उन लोगों के लिए रख लें। अलबत्ता मैं अब आप लोगों को ये तसल्ली देना चाहूँगा कि इसमें कोई बहुत ज़्यादा कॉम्प्लिकेटेड प्रोग्रामिंग इस तरह की चीज़ों की हमें ज़रूरत नहीं होगी। सिंपल चीज़ें जिसमें प्लॉटिंग है और मैट्रिसेस को यूज़ करना, और इसके अलावा कोई इंटेग्रल्स वगैरह अगर आप सॉल्व कर लें, हो सकता है करने पड़े, और उस इन सब चीज़ों के लिए वैसे मैथमेटिक्स का सबसे ज़्यादा जो है वो आपके लिए हेल्पफुल साबित हो। मोस्टली हमें ज़रूरत पड़ेगी मैट्रिसेस के लिए, या छोटे मोटे जो प्रोग्राम्स हैं, कहीं ऑप्टिमाइजेशन कहीं रन करनी है तो इस तरह की चीज़ों के लिए, और प्लॉटिंग वगैरह के लिए, लेकिन बहुत ज़्यादा कॉम्प्लिकेटेड प्रोग्रामिंग की ज़रूरत नहीं होगी।
सर आप सोर्स कोड सारे अपलोड कर देंगे?
जी जी जी। ओके, और किसी का कोई क्वेश्चन है? ओके, सो is the screen is still shared or not? Can you see this graph?
स्क्रीन नजर नहीं आ रही सर।
Let me see, because the graph is, shown up. So ये देखिए, ये 3D control plot जो है उसका आ गया. So this is actually a nice way of visualizing the orbitals in 3D, and you can see this at least outermost contour that can give you some shape of the orbital. Actually, in this contour plot, you can also just specify the number of contours and also the values of the function for which you want the contour. This is pretty flexible, and you can get a pretty good shape of the orbitals. All right, so is there any other question?
सर अगर वो आपने खोला हुआ है अभी 3D कंट्रोल वाला, तो उसमें हमें थोड़ा सा दिखा सकते हैं कि अगर हम उसको उसी वक्त ओरिएंट कर लें एक्स जी की तरफ तो फिर क्या नजर आता है, एक्स वाई की तरफ क्या नजर आता है?
Okay, I'll have to label them, but the good thing is this is a plot that is, has the same shape for 4 types of orbitals: xz, zx, I think yz, and the x square minus z square. The only difference is this, that you see this is the actually xy profile, and in the xy plane you have these lobes that are pointing along these diagonal directions. For the x square minus z square, this would just be rotated by 45 degree. But if you look in the other plane, in the along the z axis, so this is, we see that along z axis, in the center, the probability of finding it is very 0. And similarly, along this axis, along x and along y, and along all 3 axes, finding the particle is very hard. It's, very less likely. But inside each of the quadrant of the plane, the probability of finding the electron is high, which decays as we go up or down the z-axis. So this is the way of visualizing it. Okay, Bilal?
यस सर, ठीक है, थैंक यू।
सर
जी जी।
सर वो असाइनमेंट के जो कोड हैं, क्या हम उनको एक ही फाइल पे कॉपी करके अपलोड करते हैं? बिकॉज आपने कहा है कि सिंगल कोड फाइल में
बिल्कुल
अपलोड
बिल्कुल, हाँ। जो क्वेश्चन 1, 2 है उसकी एक पीडीएफ बना लें, और क्वेश्चन 3, 4 का जो कोड है वो एक ही फाइल में कॉपी करके अपलोड करना।
थैंक यू।
ओके, सो सिमिलरली अगर वैसे आप इसका थोड़ा सा डिफरेंट है, ये जो जी स्क्वायर वाला है ना, अगर इसको आप विजुलाइज करना चाहें, अभी वैसे टाइम नेक्स्ट टॉपिक का नहीं है, तो लेट मी जस्ट शो यू दिस वन इफ वी कैन गेट इट. This is x So this is a Z square orbital. So unfortunately, at the origin, since R is 0 and I have this division by 0 at some of these points, so it does complain, but fortunately it doesn't mess up the plot at the end. There are ways of avoiding this, but let's not worry about that. Okay, so while this is working out, let me set the stage for the rest of this course. So this is sort of my quick review of hydrogen atom that I wanted before we go on to the multi-electron atoms and molecular quantum physics. So from the next lecture we will start with the variational principle और उसके बाद फिर हम perturbation theory करेंगे और इन सब का aim जो है वो basically ये है कि how to introduce more complexity into the hydrogen atom and to be able to find properties of more realistic situations. For hydrogen atom we still have to add the spin degree of freedom, and then for multi-electron atoms we will have to understand how to work out the stationary states and with their energies and their wave functions. And for that we will begin with variational principle from the next class. तो उसके लिए आप लोगों में से जो वीक हैं क्वांटम फिजिक्स में, वो अगर चैप्टर 7 खुद से रिव्यू कर लें, जस्ट उसको एक दफा पढ़ लें, बहुत लाइट सी डिस्कशन है, तो वो बहुत हेल्पफुल होगी. I'll begin from chapter 8 of the textbook. So, any questions for today or for the next class? Let me talk to Abbas, or then I can let you know when we can have tutorial. Ji Zara?
Sir, I didn't get the part where you said that why we use real orbitals instead of complex wave functions with orbitals.
Okay, so if we look at p plus minus 1 wave function and pz, so pz is sort of a figure 8 along z-axis, and p plus minus 1 are donuts if lie them in horizontal plane and horizontal plane in xy plane. So they are fine. They are all three of them are eigenfunction of LZ operator and h square and L square. But when we let's say bring two hydrogen atoms closer together, and suppose they're both either in p plus or p plus 1 or p minus 1 orbitals, but when they come closer they form bonds, and they essentially is like a pz orbital, but now along the axis which is joining those nuclei, and their individual atomic orbitals are sort of figure 8 along that axis. So when we will want to describe those types of molecular orbitals using individual atomic orbitals, we will be needing orbitals that have symmetry around x-axis, because if the two nuclei of the hydrogen atom, they are lying along x-axis, our overall problem has symmetry around x-axis now. So our orbitals and everything would be should be x-symmetric. So then we will need px orbital to describe that molecular bond. So that's why we will be needing px. And similarly, if the two electrons are on py orbital, then we will need symmetry around y-axis, and we will need py orbitals. Does that make it clear?
Yes, makes sense. Thank you.
But as I said earlier, if all we have to do is just treat a single hydrogen atom in universe, then it doesn't really matter which one we use, and perhaps the p plus minus 1 are better because they are eigenfunctions of LZ operator as well. Okay, good. The other orbital is also plotted in 3D. So let's look at this. So this is the dz square orbital. You see it has a donut in the middle, and then it has two lobes along z. This is the z-axis up and down. So it is symmetric in xy plane, but in along z-axis, it's sort of a donut with that figure 8 shape. Okay, so I can upload actually this Mathematica file, and you can play around. And I have given all the radial functions and the angular functions here, so you can just use them later on. And actually, I think this file could be very important later on as well. And that's why I have set it up in a bit general sense, because we will be able to not only use many integrals and many computation using these functions, but whenever we have to visualize their different combinations, we can just use them and construct different functions in Mathematica and for solving some problems. Okay, so let me stop recording.